It's a great pleasure to give this to have this opportunity to talk about some of research I've been doing and some research I have done before. And actually, I think of this as like a kind of a full, more complete version of my job talk because I only had 20 minutes back then in February. Now I have like a full hour. And also, actually, the most motivating story of mine is actually it's pretty encouraging for me to get this award because back in 2010 when I first submitted my AMIA paper, I got consecutive 6 rejections from AMIA for 3 years. And it's been a quite kind of story for me because after this many years of efforts, of hard work, I finally got this award, which is really distinguished. I think not only because of this specific paper, but because of this consistency, because of this continuous efforts. I think for our PhD students is also a kind of a story. And also in this talk, I'll be talking about some of the previous work that have been rejected by AMIA, but later appear in some very good journals. So you can see that actually research, no matter research is is liked by someone, but not really appreciated by someone else. Finally, if you put enough efforts and you feel like this work is worth publishing, you'll finally get it published somehow. So I think this story will hopefully be encouraging. And beginning, and let me give a brief structure of this talk. I'll first talk about the big background, like big data in health and analytics, and then I'll talk about some very motivating examples to show how powerful information in medical documents, in this large-scale medical records, can give and can help clinical decision making. And then I'll show that at the background, because all this very cool and very fancy results actually have to lay on the foundation of some foundation work. And this is actually biomedical ontologies and terminologies are actually very foundational and very important in medical informatics research. Because I fortunately have done many years of research in terminologies. Also, I want to kind of present some of the work I did in my PhD studies to show later how can you use these terminologies to facilitate this higher level informatics and data mining research. And finally, I will use the very practical, very clinical relevant examples to show how can you use these terminologies and ontologies to mine data from large data set to facilitate this decision making. So hopefully, I have some time also for the future work, talk about my future agenda, and give you some kind of Q&A time. So big data, it's really trendy word, and actually in the recent years, actually specifically for this year, people are actually trying to kind of reflect in this kind of concept, saying, what does really big data mean? Because it's actually have different meaning in different kind of community. For example, in computer science community, when they're talking about big data, they often talk about like how can we kind of do this parallel processing in different computers to be able to improve the performance and improve the throughput of the data set processing. And also, in another way, in medical informatics, when we're talking about big data, we're really talking about how do we leverage the resources and technologies to be able to process the data that have heterogeneity, that are different, that are large number, really large scale, and also they are very different because you'll have claims data from the insurance companies, you have electronic health record data from hospitals, and you have survey data from CDC, and all this data, how can you leverage this amount of data to help you make better decisions? This is actually another thing. And also, it's not only about this volume, it's also about variety and the velocity. So what is the current trend of knowledge mining? Is actually I don't know if you have seen this pyramid-shaped kind of figure before, but actually this is what we usually talking about. What is big data? We're usually talking about how can we mine from this large amount of data and to mine knowledge from it and to be able to derive wisdoms. And a very simple example is that, for example, you look at patient record, you see that this patient has a HbA1c value, which is the average glucose value over the last couple months. You see that the patient's value is above 9.5 and then percent, and then you see that it's not working well. You see that this value check occurred last Thursday, and you know that this value is about 9.5 is above normal. then later you see that this occurrences of this high A1C score is associated with diabetes. And then your wisdom would be, sorry. Yeah, because I can see my screens different from this projector. So I was very.
That is very weird.
Yeah, that's very weird. And they have different synchronization issues, I guess. And then you see that this high A1C score is associated with high risk of cardiovascular disease. So actually trying to identify this association from the data you have observed in the patient records. So the overarching goal of medical informatics is to try to leverage. Is there any way that I can use wire connection to this projector? Because you can see my screens is different from.
Oh, yeah.
So, it's pretty. You use data mining, machine learning methods to derive knowledge and use this knowledge to help clinical decision making, to improve improve outcome as well as reduce cost. So actually, every day when we do research, we're thinking about how can we help those clinicians and physicians to make better decisions so that they can spend less money on patients, and patients will spend less money on their healthcare. And just to give a brief figure, about 1/5 of the American GDP are spent on healthcare, and this has to be reduced, and because of these various issues. So some hot topics in big data analytics and healthcare. Now, if you think about whole genome sequencing, like back in 2000, it was really very preventive, and very prohibitive because it's so expensive. You can see this figure that 2000, if you want to do a whole genome sequencing for a single person, you might spend over $100,000. But right now, in the year of 2014, this amount of money will be reduced to $10,000, which is actually still pretty expensive, but you can think of this as something that researchers can do because they have this big ROI grant, so they can spend a couple of dollars on sequencing the whole genome for several patients. And actually, over the years, since I started my attendance to AMIA conference in 2010, and now it's 2015, I see more and more research actually focusing on how do we leverage the genomic information. And this year, there is a large consortium called eMERGE, which is how do we leverage genomic data to help to kind of integrate genomic data into electronic health record to better facilitate this precision medicine design. And also, because we have very powerful computer right now, so we can actually do a lot of large-scale data analytics using a very complicated pipeline. So you can see this pipeline including 3 components: information extraction, this feature selection, as well as predictive modeling. So I will briefly talk about this idea in a couple of slides. And one interesting paper and very interesting work that I witnessed last year, since 2000, this is actually one of the most downloaded paper in 2015 in PubMed. You can imagine that since it's only published in 2015 April, only half year. Can you imagine how many downloads for this article it has already? About 200,000 times. It's been a very popular article. It's published by a previous colleague of mine in Columbia. What they do is that it's not hypothesis driven. They don't have any hypothesis. They just want to test how can we use this large amount of patient data to identify the association between the birth months and some conditions, medical conditions you have. And they use Columbia medical record data, which contains over 3 million patients, and they kind of put everything into this analytical platform, and they're assessing about 1,600 conditions that have some possible association with months. And they use this, what they call CWAS, and they generated several figures, and they used also PubMed articles to kind of validate how many of their associations can be validated through these PubMed articles.
I have to ask, what's the month?
Here's the month. Yeah, and you can see that they kind of stratify this analysis into 4 different categories of conditions: the cardiovascular condition, respiratory, neurological, and reproductive. So you can see that this axis is the birth month from January to December, and this is the kind of like association. If this bar is like above 0, it means that it has a higher association. If it's lower than 0, it means that it's a low risk. So you can see if you are born, like for example, November, December, you have a high risk for cardiovascular disease. But if you have a lower risk of cardiovascular disease, but if you're born in this month, you have a high risk for respiratory disease. So this is a very interesting article. If you're interested, I encourage you to go look at it. It's PubMed index, and also it's open access, so you don't have to pay anything to get this article. And of course, this kind of analysis, you can see more and more of this kind of large-scale, very fancy analysis in the coming years because of this powerful computers, because of the smart people there. So hopefully we'll see a lot of this research. So the big challenge actually in medical informatics still is that how can we understand the clinical notes more in a more smart way? How can we kind of use these free text notes to help decision making? And also, how can we derive knowledge from this heterogeneous data from electronic health record, from claims data, from surveys data, from this behavior data, and also how can we mine knowledge from social media? And actually, since I started FSU, I also work with several students here who are trying to kind of compare the terminology gap between professionals and the lay people, and how can we better facilitate the information retrieval task for lay people to give them better access to information. And I think there's just a lot of data that we can leverage right now. So it's just a matter of how do you prioritize your research agenda. So how can we really let computer understand the information? For example, we have this full text of information, like this is a kind of synopsis of the clinical trial eligibility criteria in a clinical trial document, which specified, for example, given a clinical trial, what kind of patients can be recruited and what cannot be included in your clinical trials. And this kind of information is written in free text. But nowadays, because we have this electronic record data, we want to know how can we kind of make this information computable so that we can identify the patients from electronic record in a more automatic way. We don't have to go put up our flyers and to let people know, oh, you have a study going on and I probably can be eligible, so I just go look for it. But rather, the now paradigm shift is to to be able to identify the patients automatically from the large database. And this is really challenging. And hopefully in our community, because of the efforts in the earlier researchers and investigators, they actually structured a lot of medical knowledge into terminologies and control terminologies and terminologies to help this kind of automated processing information extraction. For example, SNOMED CT is one of the most important clinical terminology in the world. It's currently being used by over 100 countries all over the world, and there's an international organization called International Health Terminology Standard Organization, which kind of maintains this terminology, and they publish this new version twice every year. And you can see the knowledge is structured in a way that you can identify their relationships. For example, they have 19 disjoint hierarchies, one for clinical finding, another one for procedure, and there's another one for device. And the concepts actually have some interactions. For example, you can see this, this is pretty blurry. For example, pneumonia is a condition. It has a relationship called finding site to this concept lung structure, which is under body structure hierarchy. So you can use a lot of information embedded in these large terminologies to infer knowledge, to be able to kind of, for example, if you're given this text saying that pneumonia and lung cancer, you can kind of extract the concept from the text and be able to identify their relationship. And this is actually also being used in America widely, because in the phase 2, in the stage 2 for meaningful use, all the electronic health records have to use SNOMED CT to encode their diagnosis and the problem lists. And also SNOMED CT, because it contains over 300,000 concepts, still because medical science is really complicated and keep evolving, so there's new concepts coming in and there are some concepts that are no longer used. They're just going to be retired. And SNOMED CT support this post-coordination, which means that some concepts, they're not encoded in SNOMED as pre-coordinated concepts. They can still be constructed using post-coordination. For example, if you have concepts like history of severe menstrual pain, you can construct this concept by 4 different concepts in SNOMED. And this is really flexible. But in other sense, because it's complexity, a lot of hospitals resist using this post-coordination because no hospital, no clinicians and physicians know how to construct concepts. So there's like an argument, whether this is good for processing or bad, because if you have different ways for constructing concepts, you will have some interoperability issue because different hospitals may come up with different set of concepts. And another fantastic contribution in the community is that actually some earlier researchers, they kind of built this system called unified medical language system, which is one of the biggest, actually it's the biggest terminological system in the world. It integrated over 150 biomedical terminologies around the world, and they kind of map the different representation of the same concepts into a unified code. For example, the concept for slow CT, myocardial fraction, and the cardiac fraction, and some concept from NCIT, National Cancer Institute thesaurus, which is a heart attack. You must recognize that this concept means the same thing, so they integrate these several terms into the same concept called myocardial fraction with a unified code. And the power of this kind of structure is that no matter how you represent a concept in a free text, you can always recognize the concept, be able to map them to a unified code. So you don't have to worry about different representations. And also UMLS has another cool feature is that it has a two-layer structure. The lower layer is a meta thesaurus, which consists of about 3 million concepts and over 30 million terms. And also, every concept in UMLS has assigned one or more than one semantic type, which represents a semantic category of the concept. And both the semantic network and the meta thesaurus have interrelated relationships between different entities. And in my previous work, in my PhD work, actually I did a lot of work in trying to correct UMLS because it's so big, it's 3 million concepts and over 90 million relationships between concepts, and a lot of processing integration is done by computer. It must have a lot of errors and inconsistencies. And however, a lot of medical researchers, they actually use this terminology for data mining, for information extraction. If you have a lot of errors, you will definitely have a lot of errors after you use this information, use this terminology for data processing. So actually we got back in 2004, we got a big all-round grant from National Library of Medicine, basically just specifically doing auditing work for UMLS, people to correct their errors, inconsistencies. So briefly, some brief idea about this work is that UMLS has 129 semantic type. Back in 2004, there was like more, 135. They kind of reduced a little bit. And their semantic types have some relationships, and they are interrelated, have a hierarchy. And the thing is that because a concept can be assigned to one or more than one semantic type, so there's a semantic uniformity issue. For example, some concept may be assigned to experimental model of disease alone, and some concept may be assigned to neoplastic process, but some other concept may be assigned to intersection of this. Like, the concept may be both an experimental model of disease and a neoplastic process. So, if you're given a specific semantic type, it's hard to say whether, the concept assigned to it is uniquely assigned to this semantic type or it could be assigned to some other semantic types combination. So what we do is that we actually constructed what we call refined semantic network, which will basically create a new intersection semantic type as long as there's some concept assigned to to this combination of semantic types. So this is not visible, of course, but basically what you can see here, the idea is that on this part is a regional semantic network, which consists only unique semantic types. And this lower part is intersection, which means that as long as a concept is assigned to one or more than one semantic types, we can construct this intersection semantic types and kind of make it like a even lower level of semantic network. But however, there's a lot of issues. And over the years, we've been auditing the UMLS semantic network since 1998. And we witnessed that the number of this red bar shows the number of intersection semantic types, which means that there are a lot of intersections back in 1998. But over the years, because of auditing work, both conducted in the National Library of Medicine, as well as we also contribute a lot of auditing methods to help them correct this erroneous semantic type assignments issue. They actually significantly reduce the number of intersection semantic types. and also they reduce this specifically those concepts, those semantic intersection semantic types, which have a relatively very few number of concepts assigned to it. Because if you have, let's say, only one concept assigned to this combination, it has a higher likelihood than those intersection semantic types, which roughly like 100 or 200 concepts assigned to it. So one simple example to illustrate how this kind of erroneous assignment can be. For example, a concept called anabolic steroids is assigned to semantic type mental or behavioral dysfunction, stereo, and a pharmacologic substance. And this combination has very few extent, which means that only very few concepts assigned to it. And our auditor just take a look at it and found this assignment is erroneous. Therefore, after this assignment is deleted, this intersection will be deleted as well. And another example is that this concept, viridafine A1 glucoside, is assigned to both carbohydrate and a chemical viewed functionally. And our auditor also deleted this assignment to chemical viewed functionally and assigned to another semantic type antibiologic, which is a grandchild for this semantic type. And after this auditing work, we can kind of help UMLS editors to correct a lot of errors in the UML semantic network. And another type of erroneous assignment is that if a concept is assigned to both semantic type A and semantic type B, where semantic type A is a parent of this one, there's erroneous assignment because this is more specific than A. So if you have assigned to B, why don't you just delete A because it's more general? So this is not wrong, this is not correct. And also, we know, because we have done this auditing for many years, we know that there's like a repeated error coming up every year. So we think that it would be nice if we can design a system which can help the editors of UMLS to correct error automatically without really digging into specific assignments. So we designed this cool system called rule-based system for making the corrections. We kind of come up 8 different categories of rules which specify saying that what combinations can be added, what combinations should not be added. And this is based upon the suggestions for UMLS editors and as well as the data that actually are in the UMLS. I will not go to too much detail. I'll just give a flavor. In case you're interested, you can go look at the paper. And we designed this online-based, web-based system, which saying like, if you tell me you want to assign a concept to these two semantic type, I will tell you whether this combination should be prohibited or should be allowed. And this is still available. You can go and check it out on this URL. And given all this medical UMLS work, we're actually using UMLS, as I said before, to extract concept from the medical notes and from clinical text. And there are 2 available tools which can facilitate this information extraction. One is called MetaMap, which is also developed by National Library of Medicine. It's also freely available and open source. Everyone can use it for free as long as you have UMLS license. And also another more complicated pipeline for natural language processing is called CTEX, which is developed by Mayo Clinic. And this is a more complicated one. I will not go to detail. So for example, if you look at this MetaMap interface, you type kind of a paragraph, it will automatically extract the concepts. For example, for this sentence, diabetes mellitus refers to a group of diseases that affects how your body uses blood sugar. It will extract a concept like diabetes mellitus from this text and given and also assign a semantic UMLS concept unique identifier. And also blood sugar also have 2 UMLS unique identifier that can be identified. So this processing can help you extract concepts from the text. And another line of work that I did in my PhD is that, besides UMLS, because it's very complicated, comprehensive terminology, also in our community we have a lot of other specific domain ontologies which can be used for annotating medical text. But however, these terminologies are very difficult very difficult for use. Sometimes it has just had too many concepts. You don't know what is that, what are they. So you want to really have a summarization tool which can help you understand the terminology structure and the semantic. And also this kind of summarization can also help you identify some errors and inconsistencies in the ontology. For example, there's an ontology called CANCO, which is short for Cancer Chemoprevention Ontology, which has about 227 classes, which are also concepts. And if you use the BioPortal tool, which is the online tool for visualizing the ontology, you can see a lot of like classes are overlapped, so you can now see them clearly. So what we do is that we constructed this abstraction network, which basically group the classes with a similar structure and semantic into a node, so that you can use a node to represent a specific group of classes. And I will not go to too much detail, but specifically we based on the the relationship, hierarchical relationship of classes, as well as the relationship that this class has to the other concepts. We can use them to group this set of classes into a smaller hierarchy. And this is how we further group, because these two concepts has no parents in this area, so we can further divide this into two separate area called partial area. This is as I said, you can also talk to me later if you are interested in this taxonomy, because this is a good summarization of ontology. And then, so you can see in the beginning I've shown this large amount of classes clustered, and now I have this nicely organized structure in which each level of classes only have a specific number of relationships to the other classes. So this is a good summarization, and we previously have shown that this summarization can be used for identifying the area with higher likelihood of errors, so that you don't have to look at one concept by one concept. You can just look at a specific node to see if there's any concepts, inconsistencies or modeling errors in that. So anyway, so after all this terminology work, after this ontology auditing work, I thought, how can we really use these ontologies for developing some clinical relevant and to help clinical research and to facilitate the clinical decision making. So after I finished my PhD, I was looking for some opportunities to be able to really use ontologies to kind of design more clinical relevant applications. So in the medical informatics research, we have a lot of data sources that we can leverage, and you can use clinical data, biomedical data, or behavioral data. And if you are thinking about, we're not we don't have any friends in our hospitals, we cannot get their data from hospitals, you can still use some electronic health record data, which are publicly available. And for example, there's a data source called MIMIC2, which is ICU database, intensive care units database, which are de-identified and they make it publicly available. This is a very rich, very important resource because it's very similar to medical records. And they also have the diagnosis code, have the lab test results, and have all the sorts of information that you need for some of the work that you might be interested in doing. And also, if you're interested in processing the medical notes, you can also use another data source called I2B2, Informatics for Integrated Biology and Bedside. And also, right now, I also see that Dr. Greg Riccardi and his colleague, his worker also working using this I2B2 data for transforming the data from Tallahassee Memorial Hospital into a Picori Common Data Model. I think this is also a very interesting resource that you can take a look at. And also, biomedical data is different from clinical data in the sense that biomedical data, when we're talking about biomedical data, we're often refer to this literature, this PubMed articles, or this full-length papers which are written by clinical researchers, not necessarily from the nurses, from physicians, because oftentimes when they're writing this biomedical literatures, they often use more rigorously, more correct language than the clinical text. So the way that we handle these different data sources is pretty different. So, and also another interesting thing is that because, as I said before, we really want to use different data sources and heterogeneous data sources to kind of harmonize them to be able to derive knowledge. So it's difficult, but nowadays we have several common data models which can help these efforts, which basically means that if you have a common data model, you can always transform whatever data you have into this common data model to use the kind of some uniform analytical tools to kind of derive knowledge from the data form. And there are two, as far as I know. One is called Odyssey. This is a consortium called Observational Health Data Sciences and Informatics. And this is a consortium, basically is a group of researchers from different pharmaceutical companies, from clinical researchers, from different researchers around the world. They convene this group and they design this common data model. Right now, they have transformed over 600 million patients' data into their common data model, and they have a really nice suite of softwares which everyone can use, everyone can download, and it's open source. You can just use this model. As long as you have clinical data in this common data model, you can use their tool to kind of visualize the data. And also there's a Picori, and this is, I will just show this figure first, and this is what they developed for this common data model, Odyssey, for OMAP data model. And you can see this figure, basically it's like a figure showing that how many patients have a specific diagnosis in your database. And if you kind of hover your mouse on a specific block box, you can see that how many patients are there, what are their mean age, what their gender distribution, etc. And this is also freely available and public online. So if you are interested, you can also talk to me afterwards so I can show you how you can access it. So let me switch a little bit to my current, my postdoc research in using ontology for facilitating this clinical decision making. And the major topic that I've been working on is to kind of analyze the population representativeness of clinical trials. And why is it important? As you may or may not know, clinical trials are basically studies that investigate how well a certain treatment, for example, it could be a medication, it could be like could be a medical device, it could be a procedure, therapy, how they work in people in treating some conditions. And it's very time consuming to conduct a clinical trial. On average, it can take up to 16 to 17 years to finish a trial, and also it may cost up to like $600 million. It's very costly, very time consuming, but however, because you cannot just enroll all the patients that you may want to kind of sell this drug to into a clinical study, so you can only enroll a very small portion of patients in your clinical study. And how well this portion of patients can represent the real-world population is crucial to kind of assess how well your results in clinical studies can generalize to this real population. And the bad thing is that there are a lot of studies that cannot generalize because their patients in the trials are not representative to the real-world population. And there was a lot of studies actually reporting this issue. And one of the studies that motivated my work is the work published in Lancet Neurology in 2004, in which the researchers compared the population enrolled in dementia studies and the real-world population that are actually in their whatever survey database or national database, and then compare, if we draw this distribution of age for patients enrolled studying dementia, we can see this is a figure, and if we draw the patient's population data in the electronic health record, and this is the data. So you can see there's a very wide age gap because the age in the real-world population of diabetes patients are higher and older than the patients that are in enrolled studies. So this actually illustrates the phenomenon of this representativeness issue of clinical trials. So before I dig into the more specific technical detail in my research, I want to first define some populations that are related with this research. The target population are the patients that you want to kind of generalize your study's results to, which means that those patients are the patients, if you have a drug in the market, you want them to prescribe, you want them to use a drug to treat their disease. And the study population are the population that are defined by clinical studies, specifying like what kind of patient do we want to recruit in the study. And oftentimes because your study, you want to prove your hypothesis, you don't want to kind of confound your hypothesis by some patients with very complicated medical conditions. So you also oftentimes want to have a relatively healthier and less risky patients in your clinical studies because you don't want them to die before they exit your study, right? So oftentimes this is different from the population that you want to target your drug to. And also even if you have this population in your study population, oftentimes after you recruit the patients, your patients, is often also different from the patient that you're looking for because, pragmatically you cannot enroll all the patients you want. You basically can only enroll the patient you can reach out to, or they can know that your study they want to reach, they want to come. So there's a difference, among these populations. And our methods previously, if you want to analyze how well a population in clinical studies can generalize to the real population, they often have to compare the patients enrolled in the study with the general patient population. And this kind of analysis cannot be done before your conclusion of trial, because before that, you don't know what patients are actually enrolled. So this is pretty delayed. And our method is to analyze the patient that can be considered in clinical trial using the clinical trial eligibility criteria, which are oftentimes available before the beginning of a trial. So this will kind of inform those clinical decision makers to know that, oh, in the beginning, already know that these patients cannot generalize to the real patient population. So why don't you just take a look at it and see that if you can prove that. So our method is that, in clinical trial eligibility criteria, there are also a different representation of the same criteria. For example, for HbA1c, the average glucose level, one can say we want HbA1c, and someone can say we use A1c, and sometimes people use hemoglobin A1c. They have all the different representations. And our innovation of this work is to use UMLS or some domain knowledge to kind of structure and recognize the differences between these different representations and to group them into the same database using the same kind of variables so that we can aggregate these different representations into the same format. And then we can draw some figures saying that, oh, if you're looking at all this number of trials, what kind of patients are they considering? So I developed this tool called Vita, which is basically can be used to say, oh, if you tell me what clinical trials are looking for example, diabetes, I can tell you what eligibility criteria are often used. For example, age, HbA1c, and BMI or glucose value, they're often used in these clinical trials. And if you select specific clinical trial study variables, I can kind of profile the population in the clinical studies. For example, this is a figure showing that for clinical trials on type 2 diabetes, what kind of patients are commonly included or commonly considered. You can see the patients, this is the distribution of trials. You can see most trials are considering patients of A1C score between 7.0 to 10%. So some patients, those patients that are lower than 7.0 are oftentimes excluded by clinical trials. And this is just a phenomenon. But we cannot do this different analysis using only clinical trial data. We have to look at the real world population, right? So our method is to kind of leverage the existing resources which are publicly available. Everyone can use that to kind of do this comparison. If you still remember this figure in a couple of slides before, I showed the different population representation, and then I use the NHANES, which is National Health Nutrition Examination Survey, to profile the patient population in the real world to see how their population is like. And then I used this Vita tool, the tool just showed before, to profile the study population of the patients that are considered by trials. And I also used the clinicaltrials.gov, which has a clinical results database, which shows that how many patients actually enrolled in trials. Use them to profile the study sample of the trial participants. And then I draw this figure to illustrate this difference. And this dashed green curve shows that what patients are considered by trials. And this blue curve shows that what patients are really like in the real world population. And this the red curve shows that what patients are enrolled in trials. You can see that many trials are considering a really relatively wide range of patients, while many patients are actually older, like they're above 65 years old of age in the real population. And most of the times, the clinical trials enroll patients around like 55 or 60, this kind of patients. And this is a visualization for HbA1c. You can see that the real-world population HbA1c score is relatively lower than the patients actually considered by trial, as well as the patients that are enrolled in trials. So this also shows the discrepancies of clinical research in diabetes in terms of this HbA1c score. And for BMI, it's better because you can see this figure aligns, better than this. So in terms of visualization, because oftentimes using visualization doesn't give you a lot of information, it's very difficult to see which variable has a better representativeness than the other. So we also previously introduced this metric, which is quantitative metric, which is also lightweight and very easily to compute how well your population representativeness for clinical trials. Just give a very simple illustration. For example, if you have this set of trials, 2 trials only. One trial is recruiting patients of age between 20 to 50. Another trial is recruiting patients of age above 20. And you have this many patients. And 10 patients are younger than 20 years old, and 60 patients are between 20 to 50, and 30 patients are above 50 years old. You want to see how well your population representativeness is for these clinical trials with respect to these patients. So we kind of, first we can divide this variable range of age into 3 different intervals based upon these threshold values. And we can set how many trials are considering this age interval and how many patients actually fall into this interval. And for different percentage, we can multiply the percentage together and we can add up all these results into a specific number. And this magic number can represent the population representativeness of clinical trials. And imagine if you have different sets of clinical trials, you can use the same metric to have different numbers, so you can know like quantitatively how bad or how good it, in comparison. So we stratify this analysis by different trial phase, and just to give a brief background, clinical trial studies, they have different phases. Phase 1 trials oftentimes is just a feasibility study, test the feasibility to test the safety, and then you go to phase 2, phase 3. And our analysis shows that in terms of age, in terms of representativeness, age actually has an increasing representativeness, while A1C has a decreasing of representativeness. And also we compare this representativeness across different medical conditions. We found that asthma has a very low A1C, GIST score for age, while heart attack and stroke has a high GIST score for age, which means that the representativeness of asthma trials are very bad, while the heart attack and stroke trials are pretty good. And we stratified by study phase. Similarly, before for all these 7 medical conditions, we can see their GIST score for age slightly increased from phase 1 to phase 3 to phase 4. But phase 4 trials oftentimes have a slightly lower because they are oftentimes post-marketing trials, which kind of they're targeting a specific group of patients to see how well this treatment is and if they have any bad side effects. And I don't have much time, but I'll just quickly go through the rest of slides. And basically, later, this is a work I just got an award from AMIA. This is a work that we kind of evaluate the GIST metric because we haven't previously evaluated it formally. And the way that we evaluate it is that we give given a patient population. If we want to know if GIST can assess the population representative in clinical trials, ideally you can use 2 different trial sets in which you know that one trial set 1 has a better representativeness than the trial set 2. So you can use the GIST metric to assess whether the value actually can give you this can kind of conform this expectation. But however, oftentimes it's very difficult to obtain these 2 trial sets because you don't know what trials have a better representativeness. So instead, what we do is that we fix the trial set and we simulate different population of patients in which we know that a certain population has a better representativeness for these trials than the others. And what we do is that we have, obviously we have this target population and we have the study population, which are specified by clinical trial eligibility criteria. And then we have this weighted target population, which basically we bring this target population of real world more similar to the study population that considered by trials. So after we bring this closer, you know that this is definitely going to be a better representativeness because it's more similar. And also you have these study samples which are recruited because recruited samples are based upon this criteria. So they must be the best represented patients in these clinical trials. So we know that we can simulate these 3 populations and we can assess the GIST score if the GIST score can correspond to this expectation. So what we do is that we use the target population and we use the normal, we normalize the weight of the enhanced sample and also use the percentage of clinical trials that are considered specific patients to weight this patient target population to sample them. So after we use this to weight, we can bring this target population closer. So we evaluate GIST score, we simulate it for 3 different variables, age, A1C, and BMI. And for each variable, we simulate it 100 times because we want to show that this test is stable. It doesn't really, it's not very different. So for each variable, we simulated this experiment for 100 times. And this is a figure showing that simulation for A1C. You can see that this blue curve is a real population, and this light blue curve is a patient enrolled in trials, and this red curve is a weighted population in which we bring this real-world population closer to this blue curve. And then we tested our GIST score. We see that this GIST score is actually also has an increasing trend. And this is a visualization for age and for BMI. You can see that for age and BMI, these 3 figures are actually pretty intertwined. So even if it's pretty intertwined, we still can use GIST to validate our methods. And this is the result for our GIST score evaluation. And you can see for each variable, this GIST has an increasing that mean value, and also the standard deviation is pretty small, which shows the stability of this test. And I have 2 more minutes to talk about this, I guess. I'll try to finish up. And after we show that we can use one variable to assess the population representativeness, we now want to know that because different variables may have intercorrelations, so we want to know how can we leverage all the variables, as many variables as we want to illustrate how can we use this to assess representativeness. So we come up with this idea of, how can we analyze this using multiple variables. And this is a figure showing that if we consider using A1C, BMI, and age together, how can we do that? And this figure, each dot represents the patients. And the color of the dot represents the number of trials considering the patients. If this dot is very blue or green, it means that very few trials are considering. While whereas if this is red or blue or yellow, it means that many trials are considering. So we kind of visualize it first, and to get some flavor of how good or bad representativeness, we can see that very, very few areas of dots actually are red, which means that they have good representations. And these blue curves and the green curves, they have a very bad representations. And we use a method to be able to kind of frame or kind of identify those areas with very bad representation, and to be able to characterize these patients. And this is a visualization for A1C and age. We can see that many patients are underrepresented. They are older than 65 years old, and their A1C is below 7.2. And we further improve our GIST metric to incorporate multiple variables. We also computed the GIST score of different trial sets. And obviously, observational clinical studies, they have a better representativeness than the interventional studies, because oftentimes they don't have a strict eligibility criteria. And then we designed these cool methods to be able to categorize these patients. We identify, first of all, what patients are considered by trials more than the others. And the blue ones means that they are very considered by few trials. And this red one means that they have considered by more trials. And we first rank them, and then we kind of separate them into 2 different groups. One group is well-represented groups, another one is underrepresented group. And then we use this group subgroup categorization to categorize those patients that are underrepresented. And then we use the well-represented to see how many patients of how many well-represented patients can also be categorized by this subgroup. And then if there are many, we can further divide the subgroup based upon some k-mean clustering of these values and to be able to subdivide. And then we'll assess again how many patients can be categorized by this subgroup. And then if we're still not satisfied, we know that maybe our definition of these 2 different groups are different, are too broad. So we can kind of separate them even more to consider only this patient to be well represented and this patient to be underrepresented. And then we use this process again until we have a satisfied threshold such that the subgroups we can identify, we can use to categorize the well-represented patient, underrepresented patient does not include any well-represented patients. And then we come up with this result saying that the underrepresented group are those patients who are relatively older. They are above 65 years old, and oftentimes their A1C is below 7.2, and these patients are underrepresented in clinical trials of type 2 diabetes. And these patients who are between 44 years old to 64 years old and who have a relatively higher A1C, they are well represented in clinical trials. And my current research is trying to identify the factor in which how can we kind of improve the representativeness of those elderly patients, because we know there's a phenomenon that oftentimes elderly patients, they're not considered by trials. Often they have huge health disparities. So my current research is trying to identify factors that are associated with underrepresentation in clinical studies. And because many older patients, they also have comorbidities and they may have more co-medications, so their conditions are very complicated. And how can we kind of factor this, kind of take all these factors into account and be able to identify some factors that's associated with them? So right now I'm using different data sets. MIMIC2, as I said, is an ICU database. NHANES is a national database. And I first assess the comorbidity index, which is to assess the risk of mortality within a year for a patient given the medical condition that he has. And also I assess the prevalence of comorbidities of this patient population to see how many trials are considering these comorbidities that are prevalent in patient population. And I perform also meta-analysis on clinical trials on these conditions. Of course, this metric CCI is not our school. It's an index designed 30 years ago by some researchers called comorbidity index. And this is a comorbidity index score code for different diagnostic category. and they have ICD-9 code, which is a coding that is used in EHR to identify patients with a specific medical condition. And in my mimic database, these are the patients that are having such medical condition. And this is the CCI distribution for different patient population. We can see that normally older patients, which are this red bar, has this is a red bar is patients who are old, and this blue bar are those patients. This red bar are the patients who are younger, and this purple bar are patients who are older. We can see that 0, which means that they're low risk, and 4 more, which are high risk of mortality. You can see that these patients have a huge difference. Like normally younger patients have more patients are CCI with CCI 0, and more elderly patients have a higher CCI score, which means that they have a higher mortality rate. And these are the comorbidities that are prevalent in MIMIC2 database. The topmost one is congestive heart failure and myocardial infarction. And however, they are only considered by 14 trials, which are very, very small because you have like 25,000 trials considering comorbidities. And this is a prevalent comorbidity in NHANES. And this is the meta-analysis on these studies. Just to give a brief flavor, most studies are interventional and some studies are observational. And in terms of interventions, most studies are considering using drug as intervention, and some of them using behavior. And in terms of primary purpose, most trials are have not specified a primary purpose. And for this trials specified primary purpose, the purpose are mostly treatment and the supportive care, etc. And also, I also reported inclusion criteria, average number of criteria in terms of inclusion and inclusion. You can see that they have a very huge differences among different trials. So this is what I want to present. And the take-home message is that big data analytics is a promising direction for improving healthcare. And also, we can leverage the large amount of patient data and different data sources to be able to really help those clinical decision making and reduce healthcare cost. Okay, so finally, I would like to acknowledge several funding support I received from my PhD research and postdoc research. My research are primarily funded by National Lab of Medicine, including 4 R1 grants, and also recently our Ontology group also got a R1 grant from National Cancer Institute. And also at Columbia, I was supported by CTSA grant of Columbia, and now I'm supported by Florida State University. I really appreciate for everything that have been given so far for all this research I've done. So that's all for the presentation. Small advertisement. Next semester, I'm going to teach this data analytics course to the undergraduate level seniors. But I'm currently, really suffering from low enrollments. I only have like less than 10 students enrolled. So I really appreciate if you can kind of advertise this course to your students to see if they're interested. I think this is going to be a very interesting course because we're going to use different data mining. We're going to introduce different data mining methods, machine learning methods, as well as several data visualization, which is going to be a very interesting course to take. So I truly appreciate if you can kind of spread the word out to your students. So that's all for my presentation. Sorry I used too much time. Thank you.